Hello students, welcome to EPG Pathshala. I am Dr. Rajiv Jain from Jivaji University Gwalior. Today we are going to discuss about a module Polyprotic acid under paper Fundamentals of Analytical Chemistry. Compounds with more than one acidic proton are called polyprotic acids. What are polyprotic acids? The compounds which contain more than one proton. Polyprotic acids contain more than 1 mole ionizable hydronium ions per mole of acids. With any polyprotic acid, the first and most strongly acidic proton dissociates completely before the second most acidic proton even begins to dissociate. Amino acids may also be titrated with either strong acids or strong bases. Polyprotic acids are specific acids that are capable of losing more than a single proton per molecule in acid-base reactions. In other words, acids that have more than one ionizable hydrogen, um, hydrogen atom or proton per molecule. The dissociation of each proton from a polyprotic acid involves a separate steps. The number of equilibrium constants corresponds to the number of acidic protons, as the number of uh, ionizable protons, the same will be the dissociation constants. For example, some of the polyprotic acids are shown in this table. These are hydrogen sulfide. Hydrogen sulfide, it has two ionizable protons. Sulfuric acid, H2SO4, it has two ionizable protons. H2SO3, sulfurous acid, two ionizable protons. Phosphoric acid, it has three ionizable protons, H3PO4, because it is H3, it has three ionizable protons. Then oxalic acid, H2C2O4, it has two ionizable protons. H2CO3 carbonic acid, it has two ionizable protons, and malonic acid also has two ionizable protons, and similarly two pK values. So polyprotic acid base equilibria, acid base equilibria, polyprotic acid bases extend treatment of diprotic acids and bases to polyprotic system. Equilibria for triprotic system uh, will be one by one. Proton will ionize. Well, first the ionization of first proton will be complete. Then ionization of second proton will start, and in triprotic acid ionization of third proton will start after second proton ionization is complete. So here it represents the K values. What should be the K value? The K value increases. The K value of first is less, but it goes on increasing, which indicates that their ionization becomes more difficult, Removal of proton is more difficult in second case, and in third case it is even more difficult. Polyprotic acids contain more than 1 mole ionizable hydronium ions per mole of acid. They ionize to give more than one H plus ions per molecule. Possible forms of three polyprotic acids are given below after their dissociation into H plus ions. These H2S. After giving one H plus ion, it forms HS anion. It further gives one H plus and it forms S2 minus anion, S2 anion. It forms, anion is formed. Similarly, in case of sulfuric acid, H2SO4, it dissociates, and after dissociation, one proton is lost and it gives HSO4 anion, and again it dissociates and give one proton and forms SO4 2 anion. Similarly, phosphoric acid, H3PO4, after dissociating a proton or H plus, it forms H2PO4 anion. Then further it loses a proton and it forms HPO4 2 anion, and it further loses a proton and forms PO4 3 anion. These acids ionize in several stages, giving out one proton at each stage. The acidity constant for these acids then may be written as K1, K2, K3 for the first ionization, first dissociation of proton, it is K1, then second K2 dissociation of third proton, it is K3. Consider a general triprotic acid H3A, any triprotic acid H3A. In aqueous solution, this acid will be distributed in four different species: the acid and the three conjugate bases. One will be acid as such and its three conjugated bases. You can see here in this example H2O when present with generic triprotic acid H3A, it forms H3O plus and H2A minus will be formed conjugate base, anion is formed, conjugate base is formed, then again H2O plus H2A anion and it forms H3O plus and Ha2 anion conjugate base again, and H2O plus Ha2 anion it forms H3O plus A3 anion. So you can see here the acid is 1. Acid is 1 as given above. H3O plus is the acid and it is forming three different conjugate bases. What are three conjugate bases? These are H2A anion, Ha2 anion and A3 anion. Each acid equilibrium has a separate equilibrium equation. Each equation in turn has a different constant. Ka1 is the constant for the first proton ionization. Ka2 is the second proton ionization. Similarly, so it continues Ka3, it may be Ka4. The acid equilibria are expressed by three equilibrium equations. Ka1 is equal to H3O plus, as you have seen in this equation, in bracket H2A anion upon H3A. Similarly, we can write it K alpha 2, K alpha 3. For all the three, we can write this equilibrium equations can be written. Another constant is beta formation constant. One can also find the formation constant or beta equations. They are found by taking products of the equilibrium equations. Beta 2 is equal to K alpha 1, K alpha 2 is equal to H3O plus ka square, Ha2 anion ka square upon H3A. Similarly, beta 3, the K alpha 1 and beta equations give concentrations of the conjugate bases in terms of only K alphas, that is Ha3A K alphas of Ha3A and H3O plus. Now consider H2S. H2S, it dissociates into H plus and HS anion, and HS anion dissociates into H plus and H2. So for both K1 and K2 equations can be written as represented above. Obviously, for the overall ionization reaction, H2S is equal to 2H plus H2 anion and K overall is equal to H plus chi square S 2 anion chi square and H2S is equal to K1 into K2. Figure 1 shows titration of polyprotic weak acid. It shows titration of polyprotic weak acid where dissociation takes place in 3 points pKa1, pKa2 and pKa3. These is the titrant and pH versus titrant titration is taking place, titration of polyprotic weak acid. You can very well understand that it is the dissociation of protons are dissociating proton 1, proton 2, and it gives the value of pK2, pK3 and pK1 by the dissociation. And we get in this titration two equivalence point, first equivalence point and second equivalence point. Two equivalence points are observed. Diprotic and polyprotic acids show unique profiles in titration experiments where a pH versus titrant volume curve clearly shows two equivalence points for acid. This is because the two ionizing hydrogens do not dissociate from the acid at the same time. With any polyprotic acid, the first and most strongly acidic proton dissociates completely before the second most acidic proton even begins to dissociate. As you can see in the from figure 2, which is the titration curve of carbonic acid, that first proton dissociates and H2CO3 dissociates into HCO3 anion plus H plus, means polyprotic acid first which and most strongly acidic proton dissociates completely. Here in figure you can observe that both two curves are not overlapping, but it is the complete dissociation of first proton, and the second proton starts when the first dissociation of first proton is complete. And in the second case, SCO3 gives a proton and CO3 anion is formed as in the case of, and these are obtained first, and point is recorded with the help of thermal blue indicator. Thermal blue indicator gives color change at the first endpoint, and at the second endpoint phenolphthalein indicator is used, which gives a color change. The titration curve of a polyprotic acid has multiple equivalence points, one for each proton. In carbonic acid cases, the two ionizing protons each have a unique equivalence point. As is shown in figure 2, each ionizing proton has an equivalence point which is observed by change in color with the help of indicators. Some of the examples are here where chemical equations for in following example you will see that there are three successive ionizations of phosphoric acid. First dissociation, H3PO4 in aqueous solution dissociates, giving the same H3O plus, and the product formed is the H2PO4 anion, first ionization or dissociation. Second dissociation produces HPO4 2 anion, and third dissociation produces PO4 3 anion in aqueous. Consequently, an aqueous solution of phosphoric acid contains all the following molecules and ions in various concentrations. What it contains? An aqueous solution of phosphoric acid will contain all the constituents. What constituents? H3PO4 itself, which remain undissociated. It will for in aqueous solution H2O, H3O plus will be there, which is formed. Some OH ions will be there. H2PO4 anion will be there. HPO4 anion will be there. PO4 anions will be there. So this is the overall concentrations of all anions present in the molecule. Some are undissociated, such as H3PO4 and H2O also remain undissociated in a small amount. The stability of the structure of the molecule sometimes plays a role in how many hydrogen ions a polyprotic acid molecule will release. Many polyprotic acids will turn into common polyatomic anions after releasing between 2 and 4 hydrogen ions. The dissociation of phosphoric acid can be represented by the three dissociation equilibria as represented by earlier equilibria. Here the equilibria K1, K2, K3. K1 will naturally be H plus into H2PO4 anion upon H3PO4, having its K1 value 5.89 into 10 raised to power minus 3. For K2, this value comes out 6.16 into 10 raised to power minus 8, and K3, the value comes out at 4.7 into 10 raised to power minus 13. The structure of phosphoric acid is given below, and from this structure you can see very well that with phosphorus 3 OH groups are attached, in which in this structure the phosphorus atom is located in the center of a tetrahedral arrangement of oxygen atoms. Tetrahedral arrangement of oxygen atom is present in phosphoric acid. When one of the protons is removed, the remaining anion, after removal of one of the protons from OH, the remaining anion has one negative charge that is delocalized over all the four of the oxygen atoms. Here it is very important thing to note that after the removal of one proton, what remains? A anion present there is left out. Anion means H3PO4. H3PO4 is ionized to H2PO4 anion, and this negative charge remained on oxygen atom, one of the oxygen atom, because hydrogen is released as proton. When the removal takes place, the remaining anion has one negative charge that is delocalized over all four of the oxygen atoms. This is the important thing to note. As a result, the removal of a second proton, now second proton is removed from an oxygen that assumes a partial negative charge is more difficult, and the removal of the third proton from the di-negatively charged species is even more difficult. So this you can see from the K1 values, K values, that the removal of proton is becoming difficult and difficult. This is clear from the values of the successive dissociation constants K1, that for K1 it is in the range of 10 raised to power minus 3, for K2 10 raised to power minus 8, and for K3 it is 10 raised to power minus 3, that the removal of proton from the di-negatively charged species is very difficult in the case of removal of third or ionization of third proton and formation of the species PO4. PO4 anion is very difficult. Distribution of species diagram. The molecule or anionic forms that a polyprotic acid assumes in aqueous solution depend upon the pH of the system, or conversely, the pH of a polyprotic acid system is determined by the forms of the polyprotic acid that are present as shown in figure 3. In figure 3, distribution curves for phosphoric acid system has been shown. Here, a plot of the fraction of the total polyprotic acid present as each species versus pH is referred to as a distribution diagram. Distribution diagram has been shown, and in this diagram, in the different regions of pH, you can see a different amount of H3PO4. H3PO4 in the first case, in between pH 1 to 3, you will find out that here H3PO4 is present along with H2PO4 anion. Whereas if we further increase the pH, only H2PO4 anion is present. Whereas if we increase pH further around neutral at pH 7, H2PO4 anion along with HPO4 anions are present. And if we further increase the pH around 9, only HPO4 anions are present. But if we further increase the pH in between 11 to 13, a mixture of HPO4 anion plus PO4 anions are present. A plot of the fraction of the total polyphosphoric acid present as each species versus pH is referred to as a distribution diagram as shown in figure 3. A graphic representation of a polyprotic system is helpful in understanding the nature of the equilibria involved. From the figure, clearly we can find out where at what pH which species is existing. The distribution curves shown in figure 1 can be used to determine either the relative amounts of species needed to prepare a solution of a given pH or to predict the pH of a system given the amount of various species. If the successive pKs of a diprotic acid differ by 3 or more, the titration curve is composite of two monoprotic acid curves as shown in curves A and B of figure 2. As the pK values approach each other, the two curves merge into single curve and the equivalence point of the first proton disappears in curves C and D. As shown in the following curve, which is the titration curve for polyphosphoric acid, polyprotic acid, here you can see there are two types or two curves A and B from where necessary information can be obtained. Here also, here these curve A, B, C, D all indicates how the proton ionizes, how it is liberated, how it affects the pK values. Here it is curve is between pH and fraction titrated. Students, again you concentrate on figure 3, which is the distribution, curves for the dissociation of phosphoric acid. Phosphoric acid is H3PO4, which contains three ionizable hydrogen atoms or protons. So at initial pH, you can see in between pH 2 around pH 2, there are two constituents present there. One is the undissociated H3PO4 phosphoric acid, and another is a dissociated species from which one proton has been removed, that is H2PO4. If we proceed further, then at the next pH range, only H2PO3 is present. H2PO3 is present, H ion has been removed. Then further, with increase in pH, further one proton ionizes, and now again two things are present, H3PO3 plus HPO3. So this is pH dependent process. With pH, the protons are being ionized, and if we proceed further, then we will find only HPO2 is present, and then again if we find proceed further, then it ionizes again PO3 anion plus HPO3 is present. If further pH is increased, if we go to pH 12 and 13, then only PO3 anions are present. So it is the continuous ionization or dissociation of uh, phosphoric acid H3PO3 one by one with pH. Protons are liberated, and as the protons, first proton is easily liberated, second proton more difficultly, and third more difficultly. So that arises in the sequence. pK values are pK1, pK2, pK3 are determined from this distribution curve. Another very important system, polyprotic system, very important system is polyamine and amino acid systems. Polyamines, which function as weak bases, are used as buffering agents and as complexing agents for metal ions. Polyamines, because they contain lone pair of electrons over nitrogen, they are frequently used as complexing agents for metal ions. In complexing medium, there is a direct competition between available protons and the metal ions to bound to basic sites of the polyamines. Thus, a knowledge of the nature of the equilibrium, acid-base chemistry of these type of molecules is essential for an understanding of their use and limitations as metal complexing agents. Amino acids may be titrated with either strong acids or strong bases because amino acids amino acids are weak bases. So for titration, they will require either strong acid or strong bases. A structure of amino acid is given below, where a proton is available and two protons from amino group may also be liberated. The titration curve for L-alanine titration curves for L-alanine are shown in figure 7. This titration curve is with NaOH and HCl. So both there are two curves. In one curve, titration is being has been done with the help of HCl and in another with NaOH. In one case, pKa1 is 2.3 and another is pK2 9.7. As you can see here, with the two curve, we can find out the titration curve, what is happening here, how titration is taking place, why two reagents are required, because we can do with one reagent. Sodium hydroxide is a strong base, so it will be titrated with OH group present there, because here OH is a weak group, so it will be titrated with that, and HCl, a strong acid, will titrate the weak base, which is the NH2, and it will remove one of the protons present there and will give a pK2 value. It comes at 9.7. So in this type of titration, where amino acids are weak acids, but they also contain carboxylic group, they also contain replaceable proton and proton form both from carbon as well as from nitrogen. So two reagents are required for titration and we get two endpoints. Aspartic acid, which is having two carboxylic group, is representative of amino acids that have more than one carboxylic group or amine group, as shown in the following figure. The various ionic and molecular states of the compound are illustrated in following figure. So it is the ionic and molecular states of the aspartic acid. Similarly, they exist in the form H3sp, AsP plus H3 AP anion, then again it will lose one proton and form H2 AP anion. It will lose further one proton and will form HP AP anion, and finally, which will be very difficult to remove proton, AP2 minus AP minus 3 anion anionic sheath form, and this is the very difficult to remove, and you can see here we will get number of dissociation constants, and if this titration is done, is to be done again with sodium hydroxide and hydrochloric acid one by one, and then we may got inflection point for each titration. So students, we may summarize which you have studied today, that what are polyprotic acids? Polyprotic acids are specific acids that are capable of losing more than single proton. More than single proton, maybe two or three, more than single proton per molecule in acid-base reactions. In other words, acids that have more than one ionizable H plus atom per molecule are such compounds called as polyprotic acids. And these compounds, polyprotic acids, and these compounds, these such type of acids has been used for number of purposes, for titrations, for this different types of acid-based titrations of amino acids are example of these. So amino acids having amino group and carboxylic group. One is acidic group is titrated with strong NaOH, and amino group is titrated with concentrated HCl. So possible forms of three polyprotic acids are given below after their dissociation into H plus ions.